Sure.
For the triangle. Yeah. Okay, we're gonna go over that this.
Okay.
Yeah, so this whole week is about isoparametric. So, yeah, I know the project I put out a little bit prematurely, but a lot of it will make more sense. Once we talk about it.
All right.
Mhm. There's paint on the desk.
On the wall that I was leaning against.
Oh no! Oh shoot! No sign on it or whatever.
No warning.
Oh man.
I got to work, but you know, to spit out charts and graphs, but yeah, I didn't really fill out. I think you're essentially supposed to write a bunch of, you know, the code, the you know, for your sheet functions for your. Okay.
All right, it's 5:30. Let's go and get started. Good afternoon, everyone. Good evening, everyone. How's everyone doing today? Good. All right, so we are in week 15, so we're very much in kind of final production for the semester. So last time we met was last Thursday, so you guys took your midterms that day. I haven't started grading them yet, but I am planning on grading them tomorrow. So I should have them all done for you guys by Thursday. Okay, so if you want to come to class on Thursday, pick up your exams. I'll have them ready for you by. Okay. All right, and so the last thing that we're doing in this class for this semester is just the final project. And so we went over the final project a few weeks ago. It is a coding project primarily, and so you'll be writing your own finite element code. And a big part of that was the isoparametric method, right? So I have one last set of lecture notes that goes over what the isoparametric method is, and how to code it. I do have one example code for you later on as well. And so, we're just working on the final project from this point. Okay. So my plan, so we have 4 more lectures left in the semester, including today. So my plan is to cover all of the concept and all the theory behind isoparametrics, do examples. We're going to do that all of this week. So we should be, and so hopefully we should be finished with all the isoparametric stuff by the end of this week. And then all of next week, I don't have anything else planned after this set of lecture notes. And so, for the rest of our lecture times, it's going to be dedicated to just working on the project. And so working on the code for the project, working through bugs and whatnot. Okay. So I highly encourage you, if not this week, then this weekend or early next week, definitely get started on your project, definitely get started on the code. Just because, I know for sure that, questions are going to come up and things are going to happen. So you want to make sure that you kind of make the most use of the time that we have remaining. So, next lectures for next Tuesday, next Thursday are going to be just dedicated office hours for the final project. So you want to make use of them. I do have my regular office hours, of course, but I am teaching 2 other undergraduate courses this semester, and they all have final projects as well. So typically my office hours for the last week can get pretty packed. And so the only time that you guys are going to have where it's just me and focus on 541 is going to be during the lecture times next week. So you want to make sure that you get enough done with your project, get enough progress so that you can ask me questions during the time next week. Okay. I will have office hours during finals week as well. Most likely they're just going to be virtual only. But again, my undergrads are probably going to be coming in asking questions about their projects as well. So make sure you make use of the time that we have in class. Okay. All right. I think that's about it. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So the topic for this week is isoparametric 2D finite elements. Okay. So we've kind of been building towards this, for the majority of the course. And in fact, if you take an FEA course kind of similar to this in most other colleges, you'll reach the isoparametric approach at some point. The reason for this is because most modern finite elements, like the ones you find in ANSYS, are based on this approach. Okay, and the motivation is actually quite simple, right? And so the motivation actually comes from the fact that, to construct element stiffness matrices in kind of the general form, that usually involves some kind of integration over an arbitrary element shape. And that goes for both 2D and 3D. Okay. But we need that integration to form the element stiffness matrix. We need the integration to form the element forcing vector, and so on and so forth, right? So 2D, 3D integration is not too bad if you know exactly what the bounds are. But when you have arbitrary shapes, it gets difficult to determine what exactly the bounds of the integration should be. So let me give you a couple of examples, right? So let's say that we have a square. Okay. And this square exists on the XY plane. Okay. So let's say one side of the square, let's say this starts at x is equal to 2, and it ends at x is equal to 5. This starts at y is equal to 1, and maybe we'll go up to y is equal to 4. Okay. And so if we want to integrate on the square, right? So we want to integrate by the shaded region there. That's pretty straightforward, right? So we know this, the entire domain of the square is encompassed between x is equal to 0 and x is equal to 5. Okay. So we're going to integrate from 2 to 5. And then the y component goes from y is equal to 1 to y is equal to 4. So we're integrating y from 1 to 4, right? We have whatever our integrand is, dy dx, right? So this is simple to do. And so when you have kind of an element that's kind of very well behaved with a well-defined shape like this, it's not that bad. In this particular case, I don't think we would need Gaussian or Gauss quadrature here. Okay, we would just integrate this straight up. But the problem is, when you're working with kind of arbitrary finite elements, especially finite elements on kind of arbitrary geometries, like the kind that you would find within ANSYS, your elements are very rarely kind of well behaved like this, right? And so you may have a situation where, maybe you have an element that looks like this. Okay. This right here would be an arbitrary element. Okay. And so if I were to tell you to integrate on that domain, right? And so to integrate on the shaded domain and choose the bounds in a way that make sure that you encompass only the domain here, it gets challenging because the sides of the shape are slanted, for the most part. Things aren't really aligned to each other. So you can't just integrate on like a box or a region of a box here because it's not simple. Okay. But this is typically what you find. And so, we call, I'm going to call this this type of element here. We'll say that this is in the physical space. So if you think back to our ANSYS activities and you look at the elements that kind of resulted from that mesh, a lot of the elements are going to look like this, right? All manner of different shapes and sizes and orientations. So if you wanted to perform an integral on this, and we think back to how we did this in 1D, right? So when we had kind of arbitrary integration bounds in 1D, what did we do? We performed a change of variables in order to get this into a more feasible situation. Okay, because ideally, if we can change variables and we can map things in such a way that we get an integration bounds that look like this, like we get a nice square, things are going to be a lot easier for us to do, right? And so, for instance, if we have a square that looks like this. And we'll go even better. We'll say the origin is centered right at the center of the square. Okay. This is going to be a lot easier for us to perform the integral because we know what that is. Okay? In particular, if we center this square right here such that the sides of the square are all length 2 and they go from -1 to 1, right? So this is -1. Or excuse me, the coordinates of this corner of the square is 1, -1. This one up here is 1, 1. This one right here is -1, 1. And this one right here is -1, -1. Okay. The integration bounds for this particular one would be -1 to 1 and then -1 to 1, right? That's how we would integrate on that domain because that's the size of the square. This is even better for us because we know that when our integration bounds are -1 to 1, then we can perform Gauss quadrature, and then that simplifies our integration significantly. Okay. All right, the question is, how do we perform this change of variables and how does that affect the integrals that we're computing? Okay. So change of variables in 1D, relatively straightforward. There's not that many steps to do. But when you do change of variables in 2D and 3D, it actually gets a bit more complicated because you're changing kind of multiple dimensions at the same time. Okay. So that's what this is all about. So isoparametric finite elements is how do we perform this change of variables, and how do we get our integrals into a form that's much easier for us to work with. Okay. And so just for the sake of naming, this other space on the right here, I'm going to call this the parametric space. Okay. So it's a space that kind of exists in parallel to the physical space, but things are going to be altered a bit just to make the integration easier for us. Okay. So, what we're going to be focusing on is this process right here. How to perform this change of variables and how to do it in a way that kind of preserves all the important qualities of our physical space so that when we construct things like our element stiffness matrix or element forcing vector, everything is still preserved and everything still kind of gives us the same numbers. It's just we just make them integration a lot easier. Okay, so that's kind of where we're going. So isoparametric elements is just a really, really fancy term for just saying we're doing change of variables or change of coordinates in multiple dimensions. Okay. All right, any questions on this? Okay. All right, one thing to note, when we do this change of coordinates or change of variables, because if you explore the space of change of variables within math, there's all different kinds of change of variables, and there's different types that have kind of different properties. Okay, and so the change of variables that we're going to be performing is one that's called 1-to-1. And basically what that means that each point or each coordinate in the physical space is going to be mapped exactly to one point in the parametric space. So there's going to be no overlap or anything like this. Or not. So, I'd say this is probably the most straightforward, at least the most intuitive type of change of variables. And so, we're just, one way that you can think of this. Another way to call a change of variables is a mapping. Okay? So we're simply just mapping coordinates or mapping points in one domain to, points in another domain. Okay? So change of variable, you'll probably hear me use different terms, throughout the next couple of weeks, mapping change of variables, and it's the same thing. Okay? All right. And also, to make things a little bit more clear as well, I'm gonna use different variables for the physical space and the parametric space. Okay. So for the physical space, we're gonna just use traditional XY here. Okay. So things are gonna be measured in X and Y. But in the parametric space, I'm gonna use the variables, I'm gonna use Greek letters, which is xi, just kind of this kind of squiggly E looking thing. And eta. So eta kind of looks like this kind of fancy N. Okay. So the x coordinate or the kind of the equivalent x coordinate in the parametric space will be xi, and then the equivalent y component will be eta, which is this one. Okay. Whereas in the physical space, we have traditional just x and y. Just because there's going to be a lot of variables kind of floating around, so I think it's I wanted just to take a second just to kind of just establish the nomenclature, establish the standards just before we move forward. Okay. All right. So how do we actually do this approach? Well, let's actually start in the parametric space, right? So in this parametric space, we have this kind of very nicely defined element with very nice values. Okay? So let's start by actually defining the shape functions for that parametric element. Okay? Everything in finite element starts with the shape functions. Okay, so for these shape functions, I'm going to borrow from our 4-point quadrilateral. So that's kind of one of the last things that we covered before the midterm. Okay. So we have 4 of them. Okay. Remember, the number of shape functions that you have per element is determined by the number of points. And since we're working with an element here with 4 nodes, we're going to have four shape functions. Okay? So n1, n2, n3, n4. And of course, since we're defining this on the parametric element, we're going to use the parametric coordinates, which are xi and eta. Okay, so n1 is going to be 1/4, 1 minus xi times 1 minus eta. Okay. And 2 of xi and eta equal to 1/4, 1 plus xi, 1 minus eta. And 3 of xi and eta is equal to 1/4, 1 plus xi, 1 plus eta. And then n4 of xi and eta is 1/4, 1 minus xi, 1 plus eta. Okay. So there's a pattern of kind of plus minuses there, and then there's a 1/4 out in front. Okay. Okay. So it's really important that we establish the shape functions first, because we're going to use these shape functions in our mapping. Okay. Or in other words, we're going to use these in our change of variables. Okay. So if you recall from our 1D Gauss quadrature, we did the exact same thing. So we used our shape functions for the 1D element, and we use those to basically drive our change of variables. Okay? So we're doing the exact same approach here. It's just that in 2D things just get a little bit more complicated. Okay. Okay. So first thing we're going to do is we need a physical mapping of coordinates in the physical domain to coordinates in the parametric domain. Okay. Let's use the shape functions. Okay, so we're going to use the shape function to form the mapping between the coordinates in the physical domain and the coordinates in the parametric. And so we're going to form functions x. So x here is going to be a function of xi and eta. Okay. And we're going to use kind of the standard interpolation formula here. Okay. So we're going to have x1 times n1 of xi and eta plus x2 n2 of xi and eta plus x3 n3 of xi and eta plus x4 n4 of xi and eta. Okay. And same thing for y. So we'll have y as a function of xi and eta. Okay. I'm gonna use a little bit of shorthand here. I'm gonna, all the shape functions are functions of xi and eta, but I'm just gonna, omit that here. So we y1 n1 plus y2 n2 plus y3 n3 plus y4 n4. Okay. Where x1, x2, x3, x4, and y1, y2, y3, y4, those are the coordinates of the nodes in the physical space for our particular element. Okay. So x1, comma y1, that's the coordinates of node 1 in physical space. Okay. And same thing for x2, y2, x3, y3, x4, y4. Okay. So actually, let me go ahead and draw that just so you can kind of visualize it, right? So we have an arbitrary element here. Let's say we have kind of a wonky looking element like this. Okay. So this is node 1, 2, 3, 4. Okay. Node 1 has coordinates x1, y1. Node 2 has coordinates x2, y2. Node 3 is x3, y3. And node 4 has x4, y4. Okay. So those are the values that we're inputting into this mapping. We're just making a separate function for x and a separate function for y. Okay. So remember, we're mapping this onto this particular element right here. It's a perfect square. Where this is node 1, node 2, 3, 4. Okay. But the difference is that in the parametric domain, we know exactly where the nodes are, right? So node 1 here is in coordinates -1, -1. Node 2 is in 1, -1. Node 3 is 1, 1. And node 4 is -1, 1. Okay. So I'm going to try to remind you of this kind of as we go throughout the next couple of lectures, because it's really important to kind of visualize exactly what we're doing. Okay. So in the parametric domain, we know exactly where all the nodes are. We know exactly how big the element is. But in the physical domain, we don't know that, right? And in fact, we're making this kind of method kind of general for any shape, for any element of any shape. Okay. That's why in the physical domain, we just have kind of generic x1, y1, x3, y3, and so on and so forth. Okay. Okay. So this is good, right? So we have kind of our physical mapping already for our coordinates, right? So that's given by these x and y functions that we have up here. Okay, one thing that we're going to need to do as part of our mapping here, because remember, eventually we're going to use these this change of coordinates to convert our integrals. And so as part of changing those integrals, we need to have our conversion factors. And so to get that, we need to take the derivatives of each of these mapping functions. So what's interesting here is that we're gonna have actually 4 derivatives here, because not only do we have 2 physical coordinates, we have x and y, but we also have 2 parametric coordinates as well, zeta and, or excuse me, xi and eta, okay? And so we're gonna take each combination of derivatives. So for example, let's take partial x, partial xi. Okay. So we're gonna take the derivative of everything in our x function with respect to xi. Okay. Remember, the x1, x2, x3, x4, those are all constants in this case. Those are just simply the coordinates of in physical space. And so the only things that we can take derivatives of are the shape functions themselves. So x1, partial n1, partial xi, plus x2, partial n2, partial xi, plus x3, partial n3, partial xi, plus x4, partial n4, partial xi. Okay. And then same thing for partial x, partial eta. Okay. So partial x, partial eta is going to be this almost the same as the expression right above it. It's just that instead of taking derivatives in xi, we're taking derivatives in eta. Okay. So x1, partial n1, partial eta, plus x2, partial n2, partial eta, plus x3, partial n3, partial eta, plus x4, partial n4, partial eta. Okay. And then same thing for y too, right? So for the y, I'm just going to write it very quickly. So we have partial y, partial xi, 1, plus 2, three, okay, then I have partial y, partial eta. It's y1, partial n1, partial eta, plus y2, plus y3, partial n3, partial eta, plus y4, partial n4, partial eta. Okay. Okay. So probably one thing you're all thinking right now is that this is getting a little bit ridiculous already. We barely started, but it's already a little bit ridiculous, right? 4 shape functions, 2 dimensions, all these kind of mappings and derivatives, and you're right? So remember that finite elements is a technique that's designed for computers to do, right? So obviously this is very tedious to kind of do by hand, but for a computer, this is just kind of a few lines of code. So just kind of keep that in mind. And so, kind of the mindset that I want you guys to have, throughout these next 2 weeks is that, eventually we're going to be turning a lot of this logic into code, right? So I mean, first of all, kind of be thinking about, how do we kind of import this into code and what that's going to look like. And 2, try to get, it's a lot of, on the one hand, it's a lot of details to kind of keep track of in a lecture like this. And the details are important. I mean, you're gonna have to implement all the details, but kind of comprehending kind of a complex kind of algorithm like this kind of comes in stages. So I'd say the first stage is kind of just broadly kind of understanding kind of what we're doing from a qualitative point of view. And then once you kind of get the overall picture, then dive into the kind of the details. Okay. So I'm presenting it to you in a way where I'm going over, I'm going over all the details as we go about it, just because logically that's kind of the thing that makes sense. But for you guys, and I went through the same thing when I first learned this. You kind of have to do this in stages. So do kind of get a broad overview first, kind of understand just what we're doing in general, and then once you get that, then go into the nitty gritty and go through all the details kind of individually. Okay. All right. Any questions on this so far? Okay. All right, so these four derivatives that we just computed, right? These four derivatives are going to be really important for us when we perform our change of variables in our integral. Okay. And so we can actually put them all together into one single matrix. So even though we have these kind of complicated expressions, right? For any given element, each of these equations here is going to result in kind of one single kind of simple expression or simple kind of a value. Right? So let's put all of these into a matrix so that it's a little bit easier for us to do. And in fact, this matrix has a very special name. So we actually call this matrix the Jacobian matrix. Okay. And so we usually denote this matrix by J. Okay. And it's a 2x2 matrix where each entry in that matrix is comprised of the different kind of derivatives. We have partial x, partial xi, partial y, partial xi, partial x, partial eta, and then partial y, partial eta. All right, so that Jacobian matrix is going to be really important. So we're going to use that kind of a lot. Okay? And one important thing for our kind of isoparametric algorithm is utilizing this Jacobian matrix, and we're going to utilize it in kind of more than one way. Okay. Okay. So the first important use of the Jacobian matrix is that this kind of provides a scaling factor. And what I mean by scaling factor is that, a lot of times when you perform this change of variables, so let me kind of scroll up here just for a second, right? So when you perform a change of variables from the physical space to the parametric space, right? Oftentimes the area or the amount of space that this element takes up is going to change, right? So the area of the square on the right side is pretty easy to determine, right? Because each side of that square has length 2. So the area in this case is 4. Okay. Whereas for the element on the left, for any arbitrary element, we don't know what that area is beforehand. But more than likely, it's not going to be 4, right? So when we perform our integral, we want to make sure we kind of preserve kind of the overall area of the original element. Okay? And so in order to preserve that area, we need to add this scaling factor to make sure that that doesn't, that no shrinkage or no expansion occurs. Okay, so we need to add a scaling factor to ensure kind of a preservation of the size of the original. So in other words, it looks like this. And so if you have a double integral, okay, and this is of some function x in the physical space. So you have some function x dx dy. If instead we wanted to perform this integral in the parametric space, which is what we want to do, okay? So our integration bounds in this case go from -1 to 1. Parametric space. Of some function f. Okay. And now we're integrating over d xi and d eta. The biggest difference between those two expressions is that the integration bounds have changed, right? And so in order to kind of make sure that our area or our volume is preserved, we need to add this factor here. Okay. And that factor is the determinant of the Jacobian matrix. So this determinant of Jacobian is the scaling factor that I just mentioned. This right here is the determinant of the Jacobian. If you remember, when we did 1D Gauss quadrature, there was a part where we had to include kind of the derivative of our map, right? So dx d xi in that case, right? This is exactly the same thing. So this is the only difference is that in 2D you have multiple variables, and so instead of taking one factor, you form a matrix and you take the determinant of that matrix. Okay. So that's the first important part, right? So we need to make sure that we include that scaling factor there in order to preserve the overall size of our domain. Okay. The other thing we can do with the Jacobian is we can actually use the Jacobian to help us convert some of the gradient or some of the derivative expressions in our original integral. So this part's really important because if you think about the derivatives in our original integral, right? So if you think back to, last week or a couple weeks ago, right? Right. So our element stiffness matrix, for instance, looks like this, right? We have the gradient of our weighting function times K times the gradient of our temperature field, okay? These gradients here, these gradients are derivatives in the physical space, right? So derivatives in X and Y. Okay. If we're going to perform these integrations in the parametric space, we can't have derivatives in X and Y. We need to perform a change of variables on the derivatives as well, so that they're derivatives in xi and eta, which are our parametric coordinates. Okay, so let me kind of show you what that looks like. So I'm going to focus my discussion here on gradient of T, but just know that the exact same thing applies to gradient of W as well. Okay, so gradient of T. Right? When we did this for kind of 2D heat conduction, we had kind of two parts of this. So we had kind of the gradients of the shape functions in X and Y, and then we had the nodal temperature values themselves. So in other words, we have this partial N1, partial X, partial N2, partial X, partial N3, partial X, partial N4, partial X. Okay. And our second row in the matrix is partial N1, partial Y, partial N2, partial Y, partial N3, partial Y, partial N4, partial Y. Okay. And then this was multiplied by our temperatures, nodal temperatures, T1, T2, T3, T4. this is a recall. Just to kind of emphasize, this is something that we've seen before. In fact, I think we covered it last Tuesday. Okay. Okay. Because the gradient of t is basically it's a vector, right? So we have the gradient or the derivative of the temperature field with respect to x, and the gradient of the temperature field with respect to y. And the way that we did that, at least in a finite element context, is we put those derivatives on the shape functions. Okay. While we left the nodal temperatures alone. Okay. So this is kind of where we're starting, right? But we can't work with this with isoparametric elements because all these derivatives are in x and y. So we need to do something about it. So we need to convert this. We need to convert this so the derivatives are in xi and eta instead. Because those we can compute. In fact, those are kind of very easy to compute. We just need to make sure we do it in kind of a consistent way, kind of a way that kind of makes sense. Okay? And the way we're going to do this is we're actually going to make use of our Jacobian. In fact, let me rewrite the Jacobian here just so that you can kind of see it again. Right, so remember our Jacobian is a 2x2 matrix. So it's partial x, partial xi, partial y, partial xi, partial x, partial eta, and then partial y, partial eta. Okay. All right. So I'm going to do a little bit of voodoo math right now. So this is a little bit of mathematical war crimes, but it simplifies our discussion quite a bit. So let's take the inverse of this matrix. Okay. Nothing bad has happened yet. There's no voodoo that's happened yet. You can take an inverse of the matrix. That's fine. What happens next is how we interpret the inverse of this matrix. Okay. Okay, so if you notice, all of the entries in our Jacobian matrix are derivatives, right? And so they're the rate of change of one variable with respect to the other variable. Okay. Intuitively, if you take a derivative and you invert it, right? And so you take 1 over that derivative, then intuitively what you get is kind of the rate of change of the other variable with respect to that, right? So for instance, let's say that we had just a simple, let's say that we had just a simple dy dx, right? So dy dx here represents the rate of change of y with respect to x, right? Or in other words, how y changes as x changes, okay? If we take the inverse of this, right? So we take this inverse, and so that's basically doing the same thing as 1 over dy dx, okay? What you're going to get from this expression is you're going to get dx dy, right? In other words, if you invert that expression, you get the rate of change of x as y changes, right? It looks like simple algebra here, but it's not really quite algebra. It's kind of more of a different way that you interpret the derivative. Okay, so we're going to use that same logic here when computing the Jacobian inverse. So when you compute the inverse of the Jacobian, it's going to flip all of our derivatives here. So now the parametric coordinates are on top, and to kind of keep things consistent, we're also going to take a transpose of this entire thing as well. So our Jacobian inverse looks like the following. So we have partial xi, partial x, okay, and partial eta, partial x. Then on the bottom row here, we have partial xi, partial y, and then partial eta, partial y. So I know that was a very hand-wavy explanation of what the Jacobian inverse looks like, but it checks out. It's just kind of explaining that from a from a more thorough point of view, would take the rest of the lecture. So, that's why I kind of chose to explain it kind of an intuitive way. But taking the inverse kind of gives us that opposite kind of relationship. Okay. Okay. So the reason we want to do this is that these derivatives on the right here, we can actually use these to convert our shape function derivatives in our gradient. So for instance, right, let's take the very first derivative here, right? So the derivative of the first shape function with respect to x. Okay. So partial n1 partial x. Okay. What we want to do, because we want to work in the parametric coordinates instead, we want to express this in terms of derivatives of the parametric coordinates. Okay. And so to do that, in order to get the parametric coordinates in there, we can do a little bit of kind of, I call it kind of reverse chaining. Okay. So in other words, partial n1 partial x, another way that we can obtain this is that we can take partial n1 partial xi, okay? And then to that, we're going to multiply it by partial xi partial x. Okay. We kind of did like a reverse chain rule, kind of multiply by one trick, right? Because if you kind of eliminate these two factors here, you get partial n1 partial x, which is the same as before. Okay. But we're not going to do that. We're going to keep it in this form just so that xi and eta are there as well. Okay. But xi is not our only variable. And so we're going to have partial n1 partial eta, and then partial eta partial x. Okay. We can do the same thing. We can do the same thing for partial n1 partial y. So I'm using n1 as an example here, but this applies to n2, n3, n4 as well. We have partial n1, partial y. And once again, we want to express this in terms of our parametric coordinates. And so this is going to be partial n1, partial xi, and then partial xi, partial y, plus partial n1, partial eta, partial eta, partial y. Okay. Okay. So what do we notice about these expressions, right? So first of all, you should notice that both sides of the equal sign are equivalent, just because, we've kind of just expanded the derivative. But if you look at these derivatives right here, right? Those derivatives right there should be very familiar to you, because we literally just saw them, 5 minutes ago. And so if you look at our Jacobian inverse, right? Those are exactly the entries of our Jacobian inverse. So it looks like we're onto something here. So it looks like we can use the Jacobian inverse to perform these kind of conversions here, okay? Because now what we have, given that we know everything that's highlighted, is that now our shape function derivatives that I'm boxing here, these are all in terms of the parametric coordinates. So given that we know all the green highlighted terms, and in fact, we are, just because, we're gonna form the Jacobian. We can put this in terms of those as well. Okay, and so if you repeat this process, so you kind of extend this together to, N2, N3, and 4, we can actually put this into kind of matrix form. Okay. All right. So what we started with is a bunch of shape function derivatives in the physical space, right? So we started with this. We started with partial n1, partial x, partial n1, partial y, partial n2, partial x, partial n2, partial y, partial n3, partial x, partial n3, partial y, partial n4, partial x, partial n4, partial y. Okay. So that's what we started with. So these are derivatives in the physical space. Okay. If we incorporate the inverse Jacobian, we can say that this is equivalent to our inverse Jacobian here. So partial xi, partial x, partial eta, partial x, and then partial xi, partial y, partial eta, partial y. Okay. We're then going to multiply this by another 2x4 matrix, but this 2x4 matrix is going to be shape function derivatives in the parametric space. This is partial n1, partial xi, partial n1, partial eta. Okay. So this right here, this first matrix right here, this is our inverse Jacobian. And then the second matrix right here, these are all shape function derivatives, but these are shape function derivatives in the parametric space. Okay. And believe it or not, what we actually want is the one on the right. Why do we want the thing on the right? So even though the one on the right seems a lot more complicated, the fact that all of our derivatives here, at least for the shape functions in the parametric space, makes them a lot easier to do. Okay. Because what's our advantage in the parametric space, right? In the parametric space, we know exactly what our element is going to look like. Our element is a square, a 2x2 square that goes from -1 to 1 in both the horizontal and vertical axes. Okay. In fact, we know exactly what the shape functions look like. And so if you go scroll back to kind of the beginning of the notes here, right? We know that the shape functions in the parametric space look exactly like this. And it's always going to be this, right? no matter what our physical space element looks like, our parametric space is always going to look exactly the same with the same shape functions, right? And so if we can take the shape function derivatives in the parametric space, that's great, because all of these expressions here, we can actually find the derivatives of them right now, actually. And in fact, let me kind of list those for you here, just for the sake of completeness. So these are the shape function derivatives in the parametric space. Okay. So we have partial n1, partial xi. This is equal to minus 1/4, 1 minus eta. We have partial n1, partial eta. This is equal to minus 1/4, 1 minus xi. Okay. We have partial n2, partial xi. This is a positive 1/4, 1 minus xi. Partial n2, partial eta. This is a minus 1/4, 1 plus xi. Partial n3, partial xi. This is a positive 1/4, 1 plus eta. Okay. Partial n3, partial eta is a 1/4, 1 plus xi. And I'll write n4 down here. So partial n4, partial xi, this is equal to minus 1/4, 1 plus eta, and then partial n4, partial eta is a positive 1/4, 1 minus xi. A little bigger just so it's easier. All right, so all of these derivatives are based on the shape functions that we already know for our isoparametric element. Any questions on any of this so far? I know they're kind of rambling for a bit. Haven't stopped much for the lectures. Okay. Yeah, so again, take a step back. So I know this looks very tedious. There's kind of a lot to do here, but remember, these are all kind of incorporated into the computer code. Okay. And more importantly, when we eventually do Gauss quadrature and we integrate this, these are going to be very easy to evaluate because we evaluate those at either fixed locations of xi and eta. All right. Okay, so now that we have the shape function derivatives and we know that eventually we're going to be replacing our gradients with these expressions, we can kind of put all this together to evaluate our element stiffness matrix. All right, so remember our element stiffness matrix looks like the following. So we have double integral of the gradient of W multiplied by K multiplied by the gradient of T dA. Okay. And so if we want to express this integral in the parametric coordinates, it looks like the following. Okay. And so this integral here is gonna be, first let me plug in for the weighting function, right? So we know the weighting function is a W1, W2, W3, W4. We have our integral here. And so because we're in the parametric space, our integral is going to be between -1 and 1. Okay. That's the main benefit that we're going for, just so we can apply Gauss quadrature. Okay. To this, we're going to multiply by a vector here, or a matrix, I should say, containing the shape function derivatives in the parametric coordinates. So this is going to be partial n1, partial xi, partial n1, partial eta, partial n2, partial xi, partial n2, partial eta, partial n3, partial xi, partial n3, partial eta, partial n4, partial xi, partial n4, partial eta. Okay. So right now we're working on the gradient of W. Okay. And then what we're going to do is we're going to post multiply this just to make sure that we are doing this kind of consistently in the physical coordinates. We're going to multiply by our Jacobian inverse. Okay. Everything that we have here is the gradient of W. Gradient of our weighting function. Okay. Then we're going to multiply this by K. K is our thermal conductivity. Strangely, the only thing that kind of has stayed the same. Okay. And then we're going to multiply this by the gradient of T. So the gradient of T, we're going to have another Jacobian inverse here. Okay. And then to this, we're going to multiply by our shape function derivatives here. So this is partial n1, partial xi, partial n1, partial eta, partial n2, partial xi, partial n2, partial eta, partial n3, partial xi, partial n3, partial eta, and then partial n4, partial xi, partial n4, partial eta. Okay. Let me zoom out so you can kind of see everything. Okay. And since this is the gradient T, we're going to multiply by the vector T1, T2, T3, and T4. So everything that we have here, this is the gradient of T. Okay. So when we make our change of coordinates to the parametric coordinates, our gradient of T becomes that. Okay. Okay. The last thing that we need to do is we need to convert the dA. So the dA, which is our integration bounds or our integration factor here. Remember, we have the determinant of the Jacobian. That's our conversion factor. Okay. And we're integrating over d xi and d eta. So this last part right here, this is our dA. Okay. All right, so let me zoom out so you can kind of see all of it in kind of one picture. Okay. All right. So obviously there's a lot going on, right? A lot of shape function derivatives, but most of these expressions here either have very simple expressions like the shape function derivatives, or they're the Jacobian, which we're going to kind of pre-compute for every element, and we're just going to make use of it as much as possible, right? So you can see the Jacobian inverse shows up twice, and the determinant of the Jacobian shows up once, right? So even though it looks like a lot of terms here, it's when you kind of put this in code, it definitely becomes easier to implement. Okay? The only thing that you guys have to really do when as the writers of the code is kind of follow the logic in terms of what's going on. Okay? Make sure everything gets computed correctly and things are inserted in the proper place. All right, any questions on this? Okay. All right, so this is essentially part one of your project right here. So part one of your final project is to basically implement the implementation of the element stiffness matrix, which is this one here. Okay, I do have an example code that does this for the 4-node quadrilateral that I posted online. But I think we'll go through this next time. Okay? Because we don't have that much time left. We just have 9 more minutes, and so I just kind of very quickly want to go over the element forcing vector using the isoparametric approach. Okay. Because even though the element stiffness matrix is probably the most important integral that we have to do, it's not the only integral that we have to do, right? So for every element, we have to form the element stiffness matrix as well as the element forcing vector. Okay? So element forcing vector, this is going to be more part 2 and part 3 of the project. Okay. So let's recall what it looks like. So for a 4-node triangle or 4-node rectangle, our element forcing vector Fe is equal to, we have 2 terms here. So we have one term that involves a thermal generation. So that is the double integral of our shape functions. And 1, and 2, and 3, and 4. Okay. So this is just a refresher. These are all in the physical coordinates. So these are x, y, x, comma, y, x, comma, y, x, comma, y. And our thermal generation function is usually S of x comma y dA. Okay. So this right here is our thermal generation term. Okay. The other contribution, so thermal generation, that's part 2 of the project. Let me make that clear. The other term that we have for element forcing vector is the Neumann boundary condition. So the Neumann boundary condition is a line integral around the boundary of n1, n2, n3, and 4. Once again, these are all x and y, right? Physical coordinate. Okay. Multiplied by our Neumann boundary condition value, ds. Okay. And the Neumann BC is going to be part 3 of the code. Okay, so for the time that we have remaining here, let's go over simply the thermal generation integral, okay? And let's express this in terms of isoparametric coordinates. you'll be glad to hear that this is actually pretty straightforward compared to the element stiffness matrix. Because one thing that you should notice here is that there's no derivatives here, right? We only have derivatives for the element stiffness matrix. And so doing the change of variables on this integral is actually a lot more straightforward. Right? Okay, so when we perform the change of variables here, we have double integral. Okay. We still have a 4x1 vector of the shape functions, but now the shape functions are going to be in the parametric form, so the xi and eta forms that we had before. Okay. And 1, and 2, and 3, and 4. These are of xi and eta, xi and eta, xi and eta, xi and eta. Okay. Another thing that you'll notice is that these integrals are with, since we're doing this in the parametric domain, these integrals are going to be from -1 to 1. Okay. So that's really key. That's kind of the most important thing about this. Okay. Next, we have our thermal generation function. So our thermal generation function originally was a function of x and y. And so into x and y, we're going to plug in our mappings. So remember, x of xi and eta and y of xi and eta, these are our coordinate mappings that we defined kind of earlier in the lecture today. Basically, what we want to do is we want to eliminate x and y from these equations, because we're not integrating them. Okay? And so when we're just integrating a straight up function like this, no derivatives, we can just plug in the coordinate mappings directly from there. Okay, the other thing that we're going to need is the determinant of the Jacobian, right? So we need to make sure that our area or our overall kind of domain here is preserved. Okay. So this right here is our preservation scaling factor. Okay. And then our integration variables here are d xi, d eta. Okay, so that is the thermal generation contribution to the element forcing vector in the isoparametric variables. Okay. There's really only kind of two steps that we have to do here. You have to plug in the mappings, so plug in the mappings for x and y, which once we kind of get to the code, I'll show you this is actually pretty straightforward. And the only thing you have to remember from there is multiply by the determinant of the Jacobian. Okay. So again, this is essentially part 2 of your code. Part 2 of your final project. Okay. So in terms of difficulty, I would say part 3 is probably the most difficult. You're probably gonna have the most trouble with part 3, just because that's going to involve a lot of kind of a lot of programming logic that that we'll go over probably sometime next week. Part 2 is probably the easiest, right? Especially after you do part 1. After you do part 1, part 2 is pretty straightforward. And then part 1 kind of in between. All right, but of course, we haven't gone over any of the implementation details yet. That'll come on Thursday, maybe next Tuesday. Maybe we'll spend some time next Tuesday talking about the code. So, all right, any final questions before we wrap it up for today? Yep.
So for the square, it's -1 to 1, -1 to 1. What is it for the triangle?
Yeah, so for the triangle, it's a little bit different. So we're going to go over the triangle next time. But the triangle basically goes from 0 to 1 and then 0 to 1 on the horizontal and vertical axes. Of course, this changes your Gauss coordinates, and so your Gauss quadrature points are going to be different for the triangle. But the same concept is going to apply. So we'll talk about the triangle next time. We won't talk about it too much because it's kind of the focus of your project. But the triangle, it looks like this. So this is xi, this is eta. And so the triangle looks like this. Where this coordinate here is 1, 0. This one here is 0, 1, and 0, 0, like that. Yeah, so that's going to change the Gauss coordinate, but we'll talk about that next. Okay, all right, so that's all we got time for today. So thank you guys for coming today. I don't have office hours tomorrow, but I have office hours on Thursday. But we'll pick up where we left off. Okay. So definitely get started on your project. You know, even though the isoparametric stuff, we're kind of still in the middle of talking about that. A lot of the other aspects of your project you can actually implement. So things like the connectivity matrix, like the Dirichlet boundary conditions, you know, all of those are kind of more or less repeats of kind of the codes that we've done before. Okay. So if you haven't had a chance yet, definitely look at the starter code. Make sure you kind of know what's going on there, and then make sure you come with your questions. Sorry. Okay. All right. Have a good evening, everybody. Yeah.
So I started. And. I read them, so you have kind of like your step by step thing. You follow it.
Yep. Algorithm.
Oh, maybe, yeah.
Uh-huh.
So in the algorithm, you make sure I show the right. Yeah. Well, the question pertains to the shape functions for the triangle.
Yep.
We're given. So we're given shape functions here. So we'll take the derivative of the shape functions. We get just with constants.
Yep. Yep. That's exactly what it is. So the triangle is actually simpler than the rectangle in terms of implementation, because the rectangle you actually still get variables. So triangles, when you take the derivative, you just end up with a constant. So it actually makes the integration actually pretty straightforward. So technically speaking, you may have already figured this out, but technically you don't even need Gauss quadrature for the element stiffness matrix.
There's 2 for loops in part 1.
Yeah.
2 for loops, the nested for loop. The second for loop, we noticed that we do nothing with the Gauss points.
Yep. No, that's a great observation. In fact, you can.
We're losing our marbles.
Yeah. I mean, technically you can do it with the loop, but it's kind of unnecessary.
Yeah, you're like
Because
multiple times here.
Exactly. But yeah, no, that's a great observation.
You know, I'll take a look what it does, like with the TikTok function, like let's see how much time it takes with the nested for loop.
Yeah.
How much time it takes that. I'll see what the difference.
Yeah, I think it's a good one.
Yes, brother.
Yeah.
Is that for additional campus?
Yeah.
It's a design construction student system.
Okay.
And ask for professional and academic reference.
Yeah.
Put you down for the academic.
Sure. Yeah. I mean, I don't know
Or know if the application closes today,
that.
so I don't know if they'll reach out or what. but
Well,
I'll let you.
okay, yeah, if they do, then I'll put in a good word to you.
It wasn't, it looked interesting.
Yeah.
I was like,
You probably teach our 102 for this, I think that's probably what it's gonna be.
it was like helping with like. It looked like it was helping stuff with campus, not like teaching.
Oh, interesting, okay. So it is AutoCAD.
Yeah, that's what it didn't say anything about teaching.
Okay. Oh, yeah, because usually, I know our 1 or 2 course usually we have a lot of tests, but this might be probably something else. But yeah, happy to do it.
Yeah, so I'll teach you about that. We'll see. 'Cause I know Anthony's teaching the lab class.
Yes.
I think he has 2 lab classes,
Mm.
but. Be interesting.
Yeah, you get a chance to see what it's like on the other side.
Yeah, so I don't know if it's a good thing and bad thing.
Sometimes you don't want to see how the sausage is.
Part of it, I don't really want to see how. It's like, sometimes I'll turn in some random junk that like I don't understand, it's like, well. And then you just have to accept like, it's like, okay, well.
That's okay. I mean, at least
you just get some stuff.
At least you're turning something in. That's honestly better than a lot of people.
Like the other, and like my, mostly my GE classes, I just turn in something and just turn it in.
Yeah,
So I was like trying to get those out the way.
yeah.
None of it, like, sometimes nothing made sense on it. I was like, oh, this is just. Like, all I need is a seat.
Yeah. But yeah, happy to be around. If they call me, I'll put it in.
We'll see. Hopefully they do.
All right, see you, Dominic.